Okay, so good afternoon again. We start from where we left yesterday, actually the day before yesterday. If you remember, we said that for a material, for a given material, the strength, the design strength is calculated according to this equation. So there is a modification factor taking into account the influence of long duration and moisture content times the characteristic strength divided by the material partial safety factor. On Monday we discussed about characteristic strength and material partial safety factor, and today we need to start by seeing a little bit more about the K-mod factor, so how to calculate the modification factor for moisture content and long duration influence. We said we already saw this when we discussed about the wood properties. If you remember, we said that unlike concrete and steel, the strength of wood, of timber, we're talking about structural timber, is affected by two phenomena. One is the moisture content, timber, and the second one is the low duration. So basically, K-mod accounts for the dependency of the timber strength on low duration. The longer the low duration, the lower the strength, and moisture content. The higher the moisture content, the lower the strength. So this is basically the dependency. So there are two different effects in the end. And in the new revision of the Eurocode 5 that we are working at the moment at the European level, it was planned to actually split this K-mod factor in two K-mod. One K-mod taking into account only the effect of moisture content, and the other K factor taking into account only the low duration. At the moment, the same factor takes into account of both phenomena. So, first of all, how does K-mod account for low duration? The idea is that the regulation basically said that we need to assign a certain load to a low duration class. What are the low duration classes? If you read here the Eurocode 5, the low duration classes are characterized by the effect of a constant load acting for a certain period of time in the life of the structure. So for a variable action, the appropriate class shall be determined on the basis of an estimate of the typical variation of the load with time. So basically, what we need to estimate the typical variation of the load over time. So we have a table. You see table 2.1 that we're going to see right now. And the actions shall be assigned to one of the low duration classes given in this table 2.1. So this is the table, directly taken from the Eurocode, but you can find a similar table also in the Italian regulation, so there is no significant change. You see, low duration class, permanent. So an action is considered permanent when the duration of characteristic load, the order of accumulated duration of characteristic load is more than 10 years. Typical example of a permanent action is obviously the self-weight. So self-weight is assigned to the low duration class defined as a permanent. Then we have another low duration class defined as a long term. In this case, you see the order of accumulated duration of characteristic load is between 6 months and 10 years. Typical examples are a storage load. For example, load of storage. If you are designing a library, for example, in this case, the variable action that you designed the library for is regarded as a long term because it's a storage. Then you have, you see, a medium-term low duration class between 1 week and 6 months. So what are the typical loads where the duration is between 1 week and 6 months? Imposed floor loads. So for example, the variable load in this room can be regarded as a medium term, and the snow load. The snow load depending on the altitude. So if you are below 1,000 meters, usually we assume that the snow load is a short-term one. So it stays there less than 1 week. Because usually, you know, even in the center of l'Aquila, because that's less than 1,000 meters, it's very random to have a snowfall which stays there with the characteristic value we're talking about, not just the 10 or 20 centimeters. The characteristic value of the snow load stays there for more than 1 week. Instead, if you are in high mountain, it's much likely that the snow load will stay in place for more than 1 week. So, snow load may be medium term or short term, depending on the altitude. And then the wind load, also the wind load may be regarded as a short term, less than 1 week, or instantaneous. Usually, the wind is regarded as an instantaneous load, as well as earthquake and fire. Earthquake, we know, it lasts, it lasts between 10 seconds and 2 minutes. Also, the fire load it lasts a bit longer. The fire load depends on the fire resistance of the structure. If the fire resistance of the structure is 60 minutes, then of course the fire load is 60 minutes duration. In general, we say that wind, earthquake, and fire load are regarded as an instantaneous type of loading. So, when it comes to calculate the design strength of timber, the first thing to do is to characterize the load duration of your actions. So you have, for example, snow load and permanent load. First of all, you need to assign each of your actions to the corresponding load duration class. Okay? This is the first thing to do. Regarding the snow, this is taken from the national Italian annex to the Eurocode, and you can see what I told you before. The snow load must be regarded depending on the site that we are talking about. I would say more than 1,000, less than 1,000 meters. And the wind may be considered as an instantaneous load, except more accurate assessments. So generally the wind is an instantaneous load. Just to keep in mind, the coefficient K mod is the ratio between the strength of wood for the actual load condition and the strength of wood in a 5 minutes experimental test. So, the strength of wood in the actual load condition, the strength of wood that you would get if you were to perform a test, an experimental test lasting 5 minutes, more or less. Okay? It's clear so far? Just a reminder that this K mod factor, that now for timber is going to depend on the moisture content and on the load duration class. For reinforced concrete, for concrete actually, it was fixed to 0.8, irrespective of the type of load. So for reinforced concrete, for the sake of simplicity, the idea was that even if you do a seismic design, or if you do a normal design, K mod is always equal to 0.8, which is not the reality, because the reality, also for concrete, if you apply instantaneous loading or very short-term loading, like in the case of an earthquake, for sure you get more than 20% strength. So you should be using K mod equal to 1. But the regulation, just to simplify, as a matter of simplification, said, at least in Italy, in other countries may be different, but at least in Italy said, okay, K mod is 0.8 for any load condition. Okay? Instead, for timber, we said we can't do so, because for timber, in order to be conservative, we should be using a K mod of 0.6, always. While instead, we will see that K mod can range between 0.6 and 1.1, even more than 1. Okay? So our design will be too uneconomical. So, in the end, we have a table from the Euro to 5, where we can find the value of K mod depending on the load duration class. Since K mod also accounts for the dependency of the strength of the moisture content, there will be different lines depending on what we can expect in terms of moisture content within the timber. So basically we will have value of K mod table for each load duration class and each what we call service class, where service class is a kind of conventional way to take into account a certain type of environment where the wood would get a certain value of moisture content. Now let's try to understand better this. Eurocode 5 assigns a timber structure to a service class depending on the type of environment. We already saw, if you remember, when we were discussing about wood and moisture, if you remember, there is not only one value of the moisture content of wood. There may be several values, infinite values, depending on relative humidity, mostly relative humidity of the atmosphere, and temperature. And also, of course, drying process. Whether your wood has been dried or not, this may make a huge influence. So, since we would have infinite possibility, that would make the problem very complex for the designers. For this reason, the regulations decided to simplify, let's say, this kind of calculation by considering basically only 3 different possibilities. So 3 different environments, not infinite, only 3 possibilities. Those 3 possibilities are called service class 1, service class 2, and service class 3. Now let's go to understand what is the kind of environment typical of service class 1. First of all, you see, note 1, the service class system is mainly aimed at assigning strength value and for calculating deformation under defined environmental conditions. And also some information on the service class may be given in national annex. In fact, we will see that our national annex in Italy provides some information about how to choose the service class. Because of course, the designer ultimately will be responsible to choose the right service class for the structure that he or she is designing for. Okay? So as a designer, we need to assign our structure to a certain service class which should be as close as possible to the actual environmental condition that we are expecting in this kind of structure. Okay? So, service class 1. Let's now focus on service class 1. Service class 1 is characterized by a moisture content in the materials corresponding to a temperature of 20 Celsius degrees and the relative humidity of the surrounding air only exceeding 65% for a few weeks per year. So service class 1 is in general characterized by moisture content fairly low, because you see that okay, temperature is 20 degrees, but the most important influencing parameter, which is the relative humidity, only exceeds 65%, which is a medium low value, only exceeds 65% for a few weeks per year. A few weeks, how many weeks? Maybe, I don't know, 6 weeks, 7 weeks. This is the kind of number we are talking about, not 20 or 30. Talking about 3, 4, 5, 6 weeks per year. Now, if you look at the notes, you see in service class 1, the average moisture content in most softwoods will not exceed 12%. So in the end, service class 1, it's a service class characterized by a wood where the moisture content does not exceed 12%. So it's a reasonably dry wood, I would say. Just a reminder that to glue the wood, you need to have the moisture content less than 14%, otherwise they don't glue the wood. Okay, now, service class 2, characterized by moisture content in the materials corresponding to a temperature of 20 Celsius degrees and the relative humidity of the surrounding air only exceeding 85% for a few weeks per year. So while before, out of 5, let's say 4, 5, 6 weeks per year, we might have relative humidity more than 65%. Now, over the same period, we might have relative humidity more than 85%. So here, as you can see, we are increasing the relative humidity, and also the moisture content in this case is increasing, because you see, in service class 2, the average moisture content in most softwoods will not exceed 20%. So service class 1, moisture content less or equal to 12%. Service class 2, moisture content in the range 12 to 20%. Okay? Last but not least, service class 3. So service class 3 characterized by climatic conditions leading to higher moisture content than in service class 2. So in this case, we get a moisture content more than 20%. This is obviously the worst class. Now, everything is very nice and interesting, but now the actual problem is to understand when we can consider a structure service class 1, 2, and 3 in a practical case. And here you can see some advice on how to do it. For example, again, you will see that also this advice is provided by the National Italian Annex to the European File. For example, if you have your wood structure is inside a heated indoor conditions. So if you are in heated and indoor conditions, then you can assume that this is service class 1.
What does it mean?
Heated? Heated means riscaldato. It depends. If there is if you can live underneath the roof, yes. Instead, if you don't live underneath the roof, in this case, no, because it's not heated. So you need to see if it's a roof where you have flat, or if you have a roof where instead you have nothing, just kind of storage area. Not always can you access the roof. You know, you can have a flat and then only the roof without any person living inside, without any flat. Okay. So, heated indoor conditions, service class 1. Then, if you have unheated indoor conditions, for example, the roof where there is no one living, in this case you have unheated because you don't have a heating system if no one lives there. So in this case you have indoor because it's protected by the rain, but it's unheated. So this would be closer to service class 2. Or outdoor conditions, so our wood is outdoor, but it's protected by the rain. So it doesn't get in contact with water. Okay? So, indoor unheated or outdoor protected by the rain. Obviously, outdoor is unheated. Must be also unprotected by the rain. Sorry, but must be also protected by the rain. Okay, other possibility. Wood in outdoor conditions, so this was service class 2. Other possibility, wood in outdoor conditions exposed to the rain. This is service class 3. So you have outdoor condition and your wood is directly exposed to the rain. Those are just 4 examples, but there may be some other examples. For example, suppose you have a swimming pool. A swimming pool, strictly speaking, you are in a sauna. Strictly speaking, you are indoor condition and heated. It's service class 1 in the sauna. You expect the moisture content to be less than 12%. If you know what I'm talking about, the sauna. You know what is a sauna? A sauna in Italiano. No, what do you expect? Which kind of moisture content? Well, if you're in a sauna, the relative humidity is 100%, close to 100%. So it's clear that we are in service class 3. Even if you are in indoor condition and heated. So you need to be careful. Specific environments like a sauna or like a swimming pool, then of course you need to look at the value of the moisture content you can expect, the relative humidity first, and then the moisture content you can expect in the water. Okay? So be careful. In general, those advice are true, but not always. Depends on the condition. So if you look at the Italian National Annex, here you have this example, very useful. You see, example of service classes, not exhaustive, so it means that we may have some other examples. They are not all here listed, but like I said before, 1, what I said exactly before, 2 exactly this, so before you see 3rd, they added here also indoor structures where there are high values of relative humidity. The case of the sauna or the swimming pool. Okay? Is that clear? Okay, now we see some examples. We start with this. Now, unfortunately, we don't see very well, but here there is a timber roof. So there is the pillar and the beams are made of reinforced concrete, precast reinforced concrete, and then the roof is made of timber. Which service class is this? Why 2?
Because he is autonomous, but
Yes, yes, because if there are no windows, so you can say, okay, it's autonomous. Or if you want it indoor, it's unheated anyway. So unheated means service class 2. The only doubt is it service class 3 because it's autonomous? No, because it's not directly in contact with water, because it's protected by the rain in some way. Okay, this one? This one is a swimming pool. We just said the swimming pool. Of course, in summertime, when you open everything, you have an airflow around, probably this would be service class maybe 1. But as soon as you close everything here, you have in winter time, this water here evaporates, and so the relative humidity becomes quite important. So if you don't have a very serious system to exchange the air, you will end up being in service class 3.
qua dice il contrario di quello che dice qui.
No, dove è questo contrario?
La struttura activa presenta di forti concentrazioni di umidità, come una piscina.
Sì.
È la classe 3, eppure sono due diverse classificazioni.
Sì, esatto.
Non corrisponde a questa.
Che è la 3?
Questa
3? 3.
Ma non era di classe 1.
No, il swimming pool no. Il swimming pool potrebbe essere di classe 1 se l'aria circola, tipo d'estate.
Okay.
Ma se no d'inverno, quando è tutto chiuso. Ok? Prego. What about this bridge? See, this is a timber concrete bridge. This is a concrete slab. Then there are some timber beams. Here there will be some shear connectors. So what is the service class here? Huh? Here we have a doubt actually, because why could be 3? There is a motor, but here you see there is also airflow. It's outdoor, but you see it's protected by the rain. Well, not always rain. If you have a very strong wind, it will bring a little bit of water. But you see here, since there is this cantilever of concrete, in general, when it rains, this should be designed to have a depth such that the rain doesn't hit this part here. So this is, of course, this is not sure. It's somewhere in between. But in this case, we could say, since there is this cantilever, if there is flow of air, you could also consider this as a service class 2. Okay? What about this?
What's one?
One. So this is an indoor and heated condition. Very clear. What about this? Why 2?
Because it's indoor,
But you see, no one is living here. So for sure it's something. Exactly. This one? You see, this is slightly different from the one that we saw before. This is a bridge, there is a river, of course, and here there is no concrete slab to protect the field. So those are completely exposed to rain. So in this case, no doubt, this is service class 3. A structure like this, how would you design here? Because very often you have a structure like this.
The first part, one part of the
Okay. Which part?
under the roof, the second roof.
This one?
No,
This one?
yes, it's class 1 or 2 because it's protected by.
Yeah, this is protected by the rain. But this part here, we could choose for sure whether to assign this to 1 and 2. What would you assign here? 1 or 2? This case here. This is outdoor, protected by the rain. 2. Then the same beam inside can be a beam with a cantilever. So one part is 2. The part inside, which is heated, is service class 1. Okay, here
same.
Two, the same. Two outside and one inside. Okay?
Just a question about this part of the root.
Yes.
The root is 7. So
This one, exactly. This one, in fact, this one should be protected. The idea is that this one should have like a plate of metal to avoid the water. Exactly, to avoid that the water touches the wood after it penetrates inside. In this case, it's two. Otherwise, it will be three. Okay? Okay, now let's have a look to the value finally. You see here, this is a table coming from the Eurocode 5. Values of K mod. You can find the same table also in the Italian regulation. So, solid timber, 3 rows, service class 1, 2, and 3, and 5 columns. Each of those is associated to a certain value of low duration, to a certain low duration class. So, you see, as you move from permanent low duration classes to instantaneous low duration classes, the K mod raises from 0.6 to 1.1. Why is that? Because low duration, shorter low duration corresponds to higher strength. Remember that when you design for earthquake, you have to increase the strength. You have to use 1.1 coefficient. I can tell you before 2008, until 2008, the Italian regulation had 1 instead of 1.1. Probably that was a mistake. And then fortunately with the new regulation now, 2018, they changed, and now again we have this, the right value, which should be 1.1. Because for a very short duration load, of course the strength is higher. Other thing to note is that, of course, when we increase from service class 1 to 2 to 3, you see 1 and 2, they have exactly the same K mode. There is no difference of K mode between 1 and 2. Instead, there is a significant difference between 2 and 3. Meaning that for 1 and 2, it's not a big problem to choose either one or the other. You will see there will be only a small difference in terms of creep coefficient between service class 1 and service class 2. But let's say that if we make a mistake between service class 1 and 2, probably nothing is going to happen. Instead, it's critical not to make a mistake between service class 3 and the other. Because service class 3, you see, there is a significant difference. Mostly in terms of creep, you will see, but 0.6, 0.5. Service class 3 is up to 0.2 lower because of the motion content. Okay? Solid timber and glue laminated timber are basically the same coefficients, and then we have all the other materials. This is the table coming from the regulation, the Italian regulations. It's exactly the same. And now we have another problem. A problem related to the fact that, in general, when we design for ultimate state, we generally don't design only for a certain action, but we design for a low combination, or for a combination of actions. You know very well, you studied in the previous course, in reinforced concrete design, that's a limit state, ultimate limit state. You have to consider the permanent loads multiplied by this load amplification factor, and then you have to sum them with the variable actions multiplied by the load amplification factor. You get your load combination, which is a combination of permanent, short-term, long-term, different load duration classes. Now, since we have a combination which involves different load duration classes, how can we choose the K mode in this case? We read what is written here from the Eurocode. If a load combination consists of actions belonging to different load duration classes, this will be always the case, a value of K mod should be chosen which corresponds to the action with the shortest duration. So underline and highlight very well this part. Should be chosen which corresponds to the action with the shortest duration. For example, for a combination of dead load and a short-term load, the K mod value, chosen K mod value, is the one corresponding to the short-term load. So what he's saying now is that suppose you have two variables, you have one permanent and one variable action. You go back to this table here. Service class 1, permanent load, the K mod factor is 0.6. Then we have the variable load, for example, let's say snow would be short term, 0.9. So we have permanent load with 0.6, and the short duration load with 0.9. Which K mod should be chosen? 0.9. The regulation says 0.9, which is counterintuitive. Because if you think about it, you could say, okay, if I want to be conservative, I take the lowest one. So I take 0.6. But instead the regulation says no. If you have two loads, you take basically the maximum K mod. So the K mod associated with the shorter duration load. Okay, it's clear? Obviously, the dependency of the timber strength on the load duration makes the design process more complex. In the sense that the most critical load condition is not always the load condition with the maximum value. What does it mean? If you remember well, when you studied the limit state design philosophy in the course that I gave some years ago, reinforced concrete design, what I was telling you is if you have different variable actions, you just assess the different values. For example, you have three variable actions, you have to consider as a fundamental load one variable action, the other two becomes combination actions. You calculate the three values of the load combination, then you take which one? You take all three to do the design, you take only one. So you have, for example, to design a roof, you have three variable actions: snow, wind, and maintenance. Okay, you do the three load combinations. You get value, for example, 100. Then you get another value 250. Then you take the value minus 60. Okay, could be this for the roof. Now the design. Then you need to design. Which value of those you would consider for the design? Think about 1 minute and then you tell me. Okay, so your answers? All. Are you sure all of them? Yeah, you could, but then you make perhaps an effort that maybe is not needed. Now we're talking about reinforced concrete. Now you see for timber is different, but for reinforced concrete, if you get one load combination 100, another one 180, the other one -20, which one would you say is the most critical one?
The shorter action.
The
Shortest action.
shortest? What do you mean?
La più breve.
No, we're talking about reinforced concrete. Forget about timber. Forget about timber. Afterwards, we think about timber. I'm talking about reinforced concrete. What you were used to do it until some months ago. The largest one. The doubt is that if you are reinforced concrete, of course you have one pushing down, the other one pulling up, you have to consider both of them, because then you need to put some reinforcement also in the other direction. But for sure, the most critical one is the one, suppose that we didn't have the minus, we have 80, 100, 200. Which one do you design for? 200. And that's it. Done. Don't need to make any other verification for 80 or for 100, because for sure the strength demand will be lower in the other case. Okay? This is for reinforced concrete. Now for timber it's not exactly the same. Why is not exactly the same? Because for timber, depending on the load combination, also the K mode is different. And also the strength is different. So for timber, you need to consider even more load combination. Suppose, for example, suppose that you have for a floor, you have only two loads. You have the permanent one and the variable one. If you were designing reinforced concrete for an intermediate floor where you have only the permanent and the variable one, which load combination would you have considered in this case? We're talking about an intermediate floor where you have the permanent load and the variable load. So the load of the people inside. So G and Q. In this case, which load combination would you have considered in the case of reinforced concrete? The fundamental load combination, which is, remember by heart the coefficient, or even if you don't remember by heart the coefficient, it would be gamma 1.3 times G1. Let's say you have only one G, just not to lose time. 1.3 times G.
1.5.
Plus, because otherwise, plus 1.5 times Q. Okay? This will be the only load combination. And then you design, and you're okay. Now, for timber, can we consider only this? 1.3 G plus 1.5 Q is enough?
Increasing by gamma mode.
K mod is on the strength side. So we have 1.3 G plus 1.5 Q to calculate the strength demand. For example, the bending moment at mid-span. And then I need to go to compare the bending moment at mid-span with the capacity. To calculate the capacity, we have to multiply the section modulus times the design strength. The design strength for timber is given by K mod times Fk divided by gamma. So the strength capacity depends on K mod. But K mod depends on the load combination. Because we said before that if you have a G and Q, the K mod that I have to choose will be which one? The one for G or the one for Q?
Q.
For Q. Why? Because for G is 0.6, for Q is 0.9. The regulation said if you have both of them together, you take the maximum. So, in other words, I calculate my MED, so let's say this is the bending moment demand, which will be a function of gamma G times G plus gamma Q times Q, and this must be compared with MRD, which is W times Fk divided, times K mod Fk divided by gamma. Okay? So, the bending moment demand depends, of course, on the load combination, but K mod also depends on the load combination. We said that for G, K mod would be equal to 0.9. No, sorry, 0.6. And for Q, for example, K mod could be equal to 0.9. Since Q is a variable load, now I'm designing for a situation where I have a variable load. But the variable load can also be not there. For example, if I'm designing a roof, most of the time on the roof there won't be any snow. Okay? Meaning that I should also consider another load combination. I should also calculate, let's see, this is MED prime. You should also calculate a moment, MED second, as a function of only the permanent load. Now, I say, okay, I do the check when there is no snow. When there is no snow, I have only permanent. Of course, this one is less than the other. But you can see here, when I calculate the resisting bending moment, I have a K mod. I have another K mod. So this K mod, this is K mod 1, this is K mod 2. So in this case, I have K mod 2. 1, sorry, this one, 0.9. In the other, I have K mod 2, 0.6. So I have less strength demand, but I also have less strength capacity. So a priori, I cannot know which one is the most critical one. Meaning that for timber structure, I must also consider some load combinations where I don't have any variable load, or I have only one part of the variable load. Because in that case, the K mod may be lower. So I have less strength demand, but I also have less strength capacity because the K mod is lower. Okay? So this makes everything a bit more complex if you want. Because if you think about, for example, reinforced concrete design, you never consider a load combination with only the permanent load. You always consider load combination with permanent or the variables. Because in that case, what really counted was the total value of the load. But in this case, can also be that in this case we can also have a situation where we are only the permanent, so the total load is lower. But of course, since K mod is lower, also the strength is lower. It's clear? Okay, now to see if you understood. Think about having two variable loads. It would be a case where you have two variable loads. For example, on the roof, you have wind and snow. How many load combinations you should consider if you have to design a timber structure where you have two variable loads? 5 combinations. What are these 5 combinations? So, F1.
F1 with snow, like the action, the basic action, azione base e il vento come azione variabile. Sì.
Okay.
The second one, the opposite. Only the permanent load.
Last one.
And no, plus gamma G per W. Sono con la quarta solo con la neve. E la quinta solo permanente.
combinations, you have to consider 5 log combinations. And then you need to calculate for each of those log combinations the K-mod factor. Okay? And then you, strictly speaking, you should do 5 verifications like this, with the different K-mod factors. Okay? It's very important to understand well this, because when we are going to do a practical work example of a design of a roof, you will see that we may get up to 20 of those combinations. Because of course, then you have a different condition, different value. So I would like that you really understand very well what you've done here, because later we will have many of those combinations. It's clear why we have to do so?
Yes, if we have a lot of load,
Yes.
is there a simplified method?
And that was the next question I wanted to ask you. What do you think? How can we simplify? Is there a way to simplify? Do we really need to bring 20, 30, hundreds of log combinations to do hundreds of course now we are using something 1,000, but anyway, it's a pity. Is there a way, what do you think? Is there a way that we can simplify? Let's have a look at this design inequality. So, MED, here this means it's a function. Okay? But if you want to make it explicit, we could say that, for example, for assume we have a simply supported beam. For a simply supported beam, maybe I can say here better. For a simply supported beam, MPD will be, let's call this FU, so FU is the load combination, ultimately mistake. Okay, this will be our, let's say, the Q that I have on my beam. So this is the beam. FU. So MED is given by FU times L squared divided by A. Right? And this shall be less than or equal to K mod W and Fk divided by gamma. Okay? Okay, now, we said before that K mod depends on Fu. So the problem is that we have two quantities depending on Fu. Fu itself here, or let's say the bending moment depending on Fu, and the strain capacity depending on Fu through the K mod factor. Now, the way that it may work in order to simplify the problem is to divide by K mod, multiplied by 1 divided by K mod here. Then you see I get Fu divided by K mod times a constant, because L squared A is a constant, less than W Fk gamma. Okay? Since this is a constant, I can bring it here. So in the end, what I found, I could manage to isolate all the quantities that depending on Fu or K mod. So Fu divided by K mod shall be less than equal to, this is kind of related to the cross section to the material. Okay? Now, suppose we have different load conditions. If I have different load conditions, like here, I would have to write another design inequality like FU2 divided by K mod 2 less than, but this quantity is exactly the same. This doesn't change. This is load independent, load condition independent. So if you call this one, for example, C constant, this must be less than or equal to C. And then if you have another one again, FU3 divided by K mod 3, always less than the same quantity C. Suppose you have another 20 of those load conditions, the constant C is always the same. So maybe we found the criteria. What could be the criteria? How can I recognize out of 20 load combinations the most critical one? Yes, but C it's on the other side. The C is the demand, if you want. Sorry, it's the capacity, somewhere related to this capacity. So before I can calculate the capacity, since you see all 20 load combinations shall be less than a constant value, out of this load combination, which one I should take? I have 20 load combination, FU1 divided by K mod 1 less than C. Then FU2 divided by K mod 2 less than C, and then FU20 divided by K mod 20 less than C.
The one with the biggest ratio.
The one with the largest ratio. So I have 20 ratio, I have 1000 ratio, I take the maximum one. So the load combination with the maximum ratio between the load combination itself and the K mod of the load combination is actually the most critical one. It's the governing load combination. Okay? It's clear? So practical application here we had before, for example here, you see 5 load combination. I calculate the 5 K mod factors. I calculate the ratio F1 divided by K1, F2 divided by K2, F3 divided by K3, F4 divided by K4, F5 divided by K5. Then I got 5 values. I take the maximum value. So the load combination with the maximum ratio is the one governing my design. Is that clear? Okay, here we have we'll say a work example. Now I don't want to do it right now because for me it's important that you understood the concept. This was the case for example, a small pillar loaded with permanent load, snow, the wind, all again in the same way. So first of all, you need to assign the permanent to a load duration class. Permanent, of course, self-weight is permanent. Then the snow is short term, and the wind is instantaneous. There are 3 load duration classes. The idea is that the hypothesis was that this pillar was heated in those conditions, meaning service class 1. And then you see from here solid timber, service class 1, you get the value of K mod for permanent, for short term, which is the snow, and for instantaneous, which is the wind. Then, in order to calculate these load combinations, we need to know the combination coefficient, size 0, for wind 0.6, for snow 0.5. So, critical load conditions. Strictly speaking, we need to write all those 5 load conditions that we discussed before. So, start with this one, F1. The F1 is the snow as a basic load. So 1.35G plus 1.5Q plus 1.5 size 0 times W. Size 0 is 0.6. You get 108.3 kilonewton. Then we can calculate the sigma. Remember that for timber we said that usually we do the verification at the local level, so we calculate the maximum stress in the wood and divided by A, by the area, so 10.8, and then FD1, the design strength with K mod. K mod is the maximum, so 1.1, because wind is the shortest one. You get to 13.5, and you get that the verification is satisfied. Then you can do exactly the same, combination number 2. You get again verification satisfied. Permanent snow, combination here goes to the number 4. Again, verification satisfied. Permanent wind, number 3, again satisfied. And then only permanent node, since the K mod here is much lower, you consider only 1.35G, you find that in this case the verification is not as satisfied. Why? The standard band is lower, but also the strength capacity is lower because the K mod is lower, 0.6. As we said before, now that we know the trick, we understood we don't need to do all the calculations, all the verification, we just need to calculate the 5 node combination, those values. We need to calculate the K mod value, and then we do the ratio. Of course, this is true for any kind of verification, for bending, for axial force, for shear, and so on. If we had done in the previous example this ratio, we would have discovered immediately that the last one was the most critical. Because you see, the last one, 130.5 kilonewton against much lower values for the other combinations. Okay? What is usually the most critical load condition? Of course, it depends case by case, but I could say that usually permanent with imposed load, snow load, for floor roof member are the most critical one, and permanent with snow and wind or earthquake for the entire structure. Okay. Now, if you look at the Eurocode, you will find that there is actually another K coefficient. So, strictly speaking, when we write the strength of timber, you can consider another K coefficient. So, Fd equal to K6 times K-mod times Fk divided by gamma m. What is the K6 coefficient? K6 coefficient is a system strength factor for load sharing. The system strength factor for load sharing accounts for increases in strength in structural systems due to load sharing between elements because of less variability of both F and E. What does it mean this? Basically, it means that suppose you have a member made of different members connected together with some bolts, or maybe nailed together. So rather than only one element, you have many elements connected together. So since these elements are connected together, they work more as a system than independently. What does it mean? It means that if I apply a point load on one beam, it's not only that beam responding. All the beams respond because they are connected together. Okay? So basically, if we have a system, we can expect a larger strength of the system due to the reduced variability of the system itself. Think about, for example, you have 4 beams, like in a bridge, you have a concrete slab above it. If you apply a load here, the situation is completely different from the situation here, where you have only a small plank connected to the timber beam. Think about applying the same load here and applying the same load here. What would be the difference?
The capacity to distribute.
Exactly, the capacity to distribute the load here is almost zero. So here you would have, as an effect, a deflection of this beam here, and the other that would be hardly loaded. While instead here, since you have a strong member, this load is going to be applied on all these beams. So all of them, they are some way loaded together. So they act basically like a plate on a spring support. So in this case, just remember, thinking to the fact that in timber, we can have a significant variability of properties between the different beams. If you remember, we have a large scatter of results, meaning that we have 4 beams, we may have one beam very strong, another so and so, another middle, another very low. Okay? Because of the scatter of the material, it's not very stiff. So, suppose that you have a weak beam here and a weak beam in this system here. Okay? You may have because it's round, you know. So you have if you have a weak beam here, what's going to happen? It's going to happen that this beam is going to fail much earlier because it's a weak beam. If you have a weak beam here, since there is this system able to transfer the load to the other beam, what is going to happen is that it's going to transfer part of the load to the other beam. So we don't have only one beam resisting, but we have a number of beams. And since usually, if you remember, there is a correlation between the module of elasticity and the strength, if this is a weak beam, usually also the module of elasticity is lower. Okay? Meaning that this spring is more, it's a softer, the spring. So what is going to happen is that most of the force is actually going to the other beam, the strongest one, because they're also stiffer, so they attract more load. So in the end, the situation is much better than this, because we have a system effect. So we have a less scatter of results due to the system effect, because the different pieces of wood with different strength, they are forced to work together. While instead here they work separately. The fact that they are forced to work together means that the system has less variability compared to the single beam. So the more beams we connect together, the higher strength. Why higher strength? Because we have less scatter of results. So less standard deviation. Okay? So the Gaussian function is tighter, and so the characteristic value increases. So the regulation takes into account this increase in characteristic value with this K-system factor. How big is K-system? Usually you see 1.1, provided a continuous load distribution system is capable of transferring the load from one member to the neighboring members. So 1.2 up to 1.1. Sorry, 1.1. These are some examples, both with timber connectors and load characteristic elements. And you can see here, this is a table taken from the Eurocode, saying that, you see here, this is a plot providing a K-system factor depending on the number of loaded laminations. So if you have only one beam, the K-system is 1. So we have no system effect. If you have 2 beams, you see the K-system is going to increase. The more beams work together, the better. And you can see up to 8 lamination, we have an increase, and after the K-system is constant. So we can get up to 1.2 This would be in the case of lamination, pre-stress or glue together. So planks glue together. Or up to 1.1 if we have 1.1, this will be system number 1, will be basically nailed or screw lamination. Okay? And then we have a last factor that we already saw, if you remember before, which is called KH, size effect factor. The size effect factor is used to increase the tensile and bending strength of timber glulam with depth at 150/600 millimeter. So if we have some timber where the depth is less than 150 millimeter, then we can increase the strength using this KH factor up to 1.3. Instead, if we have a glulam beam with depth less than 600 millimeter, we can increase with this factor here, which is up to 1.1. So in conclusion, if you want, here we have summarized the formula with all the coefficients to work out the design strength of timber. So design strength of timber is the product of the system factor times the size effect factor times the modification factor times the characteristic strength divided by partial safety factor. Okay? So this is the formula that we are going to use in our design to calculate the design strength. Very often, this is assumed equal to 1 to 7. Okay, now we need to consider all the different cases, if you want, of the descendant problem to see how we can, some way, adapt those cases to the case of timber. So, first case, tension parallel to the grain. Tension parallel to the grain, you see we need to calculate the strength demand. So sigma T0D. So sigma is the stress, T stands for tension, 0 stands for parallel to the grain, and D stands for design. So due to the design effect. Less than or equal to the strength, tensile strength of wood parallel to the grain. Sigma T0D, we calculate very simply by dividing the axial force by the area, the cross-sectional area, while instead FT0D, you see, is given by this complete relationship. I forgot to tell you that KH, but I mentioned before, I just wanted you perhaps to focus a little bit more on this. KH can only be used for verification in tension and bending, not for other cases. So KH is different by 1 only for tension and bending. Okay, so this is tension parallel to the grain. Obviously, we need to remember that FT0K, so the characteristic tensile strength of timber parallel to the grain, will be provided by the regulation depending on the strength class of timber. Okay, you remember this is a big table showing for each strength class the value of the strength. Okay, basically here you see. Tension parallel to the grain, depending on the strength class, you get your value. Okay, compression parallel to the grain. The verification formally is very similar to the one that we saw before, if we don't have buckling, except that in this case, of course, we have a difference. You see the KH has disappeared now. It's no longer that because we're talking about compression. And we have FC0K, characteristic compressive strength of timber parallel to the grain. And the value, of course, is different. Now we need to look not for tension parallel, but for compression parallel. You can see we get almost twice as large value as large as before. For example, for C18 we have 18 in compression, 3 megapascal, and only 10 in tension. Okay? Okay, this is true if we have a swap member which doesn't have any problem of buckling. But if you remember, last time we said on Monday that we can expect quite significant buckling problems on timber beams. You remember why? Why are we expecting buckling to be a problem for timber?
Because the critical load.
Because the critical load is low. And why the critical load is low? Sorry. Why the critical load is low?
Because of the model of elasticity.
Because of the model of elasticity. Because we said that timber member as what as reinforced concrete member, but the model of elasticity is 1/3. So also the critical load is 1/3. Okay? So we can expect to have significant problem of buckling, flexural buckling in compression. Flexural buckling is instabilità carica di punta, in time. So, to study buckling, flexural buckling, you remember you learned the omega method in mechanics of structures. In this case, we use a similar method. It's not really the omega method, but it's similar as philosophy. In the omega method, if you remember, what you had to do was, you remember, how did you do the design with the omega method? Can some of you remind me? If you have a column loaded by a load P, how did you study the safety of this structure? By using the omega method, you remember?
By entering a function
Yeah.
with 2 parameters.
Yes, which function with the parameters?
D and omega.
No.
D and n.
Mm.
And to interpolate a function.
Yes.
One of
The variables?
Il punto che incrociava con 2 variabili fissando mi dava l'omega con il quale poi.
Okay, so what did you need the omega for? Once you get, okay, first of all, to get the omega, which quantity did you need to know?
L'ordine di grandezza.
No, which quantity, which variable to calculate the omega? I think you were defining a specific parameters with a Greek name. Greek name with a Greek symbol. So, I don't know, maybe you study with different symbols, but anyway, let's say, okay, you got your omega value. Once you get the omega, what do you do with this omega?
Tu dimensioni.
Yes, but, okay, physically, which formula do you use? M?
Moment.
We're talking about this one. With the moment, you were doing with the moment, the verification?
No.
N, okay, so N?
On D.
D? This way?
0.85.
Where is 0.85?
At the
Denominator or numerator?
denominator.
Then?
B.
Eh?
B.
Bigger?
B.
B? No, where is B?
Denominator.
Yes?
Resistenza a compressione, FC.
Where is it? See? And then?
Uguale a S per AY.
What is S?
AS per l'area dell'armatura.
Ah, but this we are talking about reinforcement now. What is AS? Reinforcement?
L'armatura in zona tesa in zona compressa.
Yes, but you haven't studied this with Professor Luongo. No.
No.
Yeah, I know, but now we're talking about omega method. The omega method, not the other one. The omega method. The omega method, the one that you studied with in the mechanics of structures. Anyway, what I remember when I studied the omega method was still in the high school, like for the geometry. We studied this way: sigma max equal omega n divided by a less than or equal to sigma permissible. This is what I studied. I don't know now if they changed something in the meantime, but this was this was the equation that I studied. Did you study? Did you remember? Some years ago, some of you might have nightmare thinking about this kind of thing, but okay, yes, could be the gamma of the omega. So, but always here. Was it here or was somewhere else? Was here. Okay, so omega method or gamma method, the idea was I calculate the slenderness ratio of my structure. What is the slenderness ratio? Slenderness ratio is usually denoted with lambda. Is the ratio between the length divided by radius of gyration, raggio di inerzia, rho, which is square root of second moment of area divided by A, cross-sectional area. So the original omega method was, first of all, I calculate the slenderness ratio. Then, based on the slenderness ratio, I calculate omega, which is a function, a certain function of lambda, is stable. And then I run this formula, I increase the sigma to take into account that I have a problem buckling. And then I check that the design related quality with the sigma permissible is always satisfied. Okay? This was what I studied several years ago. I call it an omega method, gamma method. Now instead, talking about timber, if you look at the Eurocodes, there is a slight change in this formulation, in the sense that you see now the verification is sigma C0D, so design compressive strength of timber parallel to the grain less than or equal to, let's say it again. Sigma C0D is the strength demand in compression parallel to the grain, and this should be less than or equal to the design strength in compression parallel to the grain multiplied by a strength reduction factor. So if you want, this inequality here is similar to this one, except that you see, rather than using the omega here or the gamma here, you put the omega gamma here. So basically, we divide by omega, we get that sigma max equal m over a. This shall be less than or equal to 1 over omega times sigma permissible. This 1 over omega is what is called Kc. Okay? So, how does it work? If we have a slender member in compression, first of all, we need to find out the slenderness ratios of the member. Why am I talking about slenderness ratios? Because we need to consider always both directions. Always. If we are sure that the restraint is cylindrical, so you have the same restraint in a different direction, then you can go directly to consider only one. So basically, the plane where you have the maximum slenderness ratio. But if you have different strain conditions in a different direction, then you need to work out both slenderness ratio. So lambda y and lambda z. Let's make a bit of order here. Suppose you have a column done in this way. So this is a timber column. Here you have a load. B. Here you can assume that here the cross section here is pin. And here also is pin. This is L, the length. This is B, and this is D. And this one, L divided by 2, L divided by 2. Okay? Also this. So this is kind of a situation that we have. And we have to check the buckling of this column. How should we do it? So, you see, sigma C0D, this is the strength demand parallel to the break compression. So sigma C0D is given by what? In this kind of structure here. P divided by
BD.
Yes, the area which would be basically B times D. Okay? This must be less than or equal to K Cy times FC0D. Cy, you see, this is the cross section. This is Y, and this is Z. So, Kcy is a reduction coefficient taking into account the buckling of the column around the y-axis. So we're talking about buckling around y-axis. What does it mean around y-axis? Does it mean that is this cross section going to displace parallel to Z or parallel to Y? If I'm talking about buckling, flexural buckling around the y-axis. So it's going to displace, it's going to move where? Which direction? Y or Z? Z. So we need to be careful here when we talk about, you see, KCY, which means the reduction coefficient taking into account buckling around the y-axis, meaning that the cross section is going to move parallel to Z, not parallel to Y. Okay? Then we need to do the other verification, sigma C 0D, is given by the same value, P divided B per D, less than K CZ times FC 0D. And this time KCZ is buckling, a reduction coefficient for buckling around the Z axis, meaning displacement of the cross section parallel to Y. Okay? Remember that for buckling you don't have the KH anymore, as before. Now, how can we calculate this coefficient KCY and KCZ? We have some formula. Those formula have been derived from the theory of the buckling, the flexural buckling of column with defects. So, in mechanics of structure, during the last degree, you learn the solution, the Euler solution, which is true only if you have a perfect beam, a perfect column, which means a column without any defect, perfectly straight, with no residual stresses and no eccentricity of the load. Okay? Now, if you are attending also the course of stability and bifurcation of equilibrium, you will learn, at least I think that you are going to learn also how to adapt the solution for the ideal column to the case of a real column, where you have an initial curvature, for example, due to the defect of the beam, because no timber member is completely straight. Timber member always a small initial curvature, take into account the eccentricity of the load, and take into account the presence of defects inside. KCY, you see, depends on KY and lambda rel y. Now, KY depends again on the relative slenderness ratio, this lambda rel y, and also depends on the coefficient beta c, which is a factor for members with a straightness limit defined in section 10. So basically beta c is a coefficient taking into account the initial curvature of the timber member. So when you buy a timber member and they want to measure, you will find that hardly ever the timber member is completely straight. But you have some like a small curvature like this. The small curvature, due to the production, due to the cutting the wood and so on, the small curvature depends on the type of material. It's smaller for wood, for engineering wood products like Lulam. See, Lulam and LBL, this beta is 0.1, is higher for solid timber, 0.2, because it's a natural material that has more defects inside. So this is a defect of straightness of the member. So this formula takes into account the this defect of straightness, and also this K factor depends on the slenderness, on the relative slenderness ratio. The relative slenderness ratio, you see, is the ratio between the slenderness ratio, the one that you defined, that we saw before, the slenderness ratio of your member divided by pi times characteristic strength of timber parallel to the grain divided by the 5th percentile of the modulo of elasticity of timber parallel to the grain. So, basically we said that K, we go back, KCY is given by this relationship, KY is given by this relationship here, and it both depends on the relative slenderness ratio. The relative slenderness ratio depends on the slenderness ratio delta, the lambda y. Lambda y, now we want to write the slenderness ratio lambda y. So lambda y is the slenderness ratio of our column around the y-axis. So slenderness ratio, we said before, is defined as the ratio between the length of the member and the radius of gyration, rho y. So we say L0y divided by rho y, which is L0y. Rho y will be given by what? So the radius of gyration around the y is given by which ratio? We have to do a ratio between the second moment of area and the cross-sectional area. Second moment of area will be the second moment of area around the y-axis. So it will be Jy divided by B times D. Okay? Well, Jy is BD cubed divided by 12. So in the end, lambda y equal to L0y divided by BD cubed 12 divided by BD is basically D squared 12. So in the end is D divided by square root of 12. Radius of gyration of the member. Okay? Now, what is the value of L0y? So for a structure like this, which value of L0y I need to use when calculating the slenderness ratio? What do you think? YL and not L divided by 2, since there is this member here.
In Italia.
Okay, in Italia. After we translate.
Perché ovviamente la lunghezza di proiezione.
And this one is supposed to be lunghezza di manifestazione.
Però là cosa fa così?
So, the question is this beam across the column able to reduce the length when this is going to buckle? Actually, we're talking about buckling of this around this axis here. So we're talking about buckling out of plane. So this one is going to buckle in this way. Okay? So is this member here able to restrain the column from buckling out of plane?
No.
No. Why?
In the other side.
In the other side, yes, but it does, but not out of plane. So I agree with you. So this is fine. So this one, L0y is basically L. Okay?
In the other way.
In the other way, now we're going to write L lambda x. Lambda x is what we need to, sorry, lambda z. Lambda z. Lambda z is what we need to calculate lambda Lz and the other k, where is it? Yeah, is kcz. Now, lambda z, now we're talking about buckling, you see, around z. Buckling around z means that this time, this column wants to buckle in the other direction. In this other direction, if this member here is fixed, it's not free, but it's connected to a fixed structure, then what would be the length to consider in the formula? L divided by 2. So this would be L divided by 2 divided by, in this case, what is the radius of the gyration, the other direction? Then we're talking about around Z. So I need to do JZ divided by B times D. So if I do the calculation, before I had D divided by a square root of 12, now I'm going to get B divided by square root of 12. So in this case, we have a situation like this. Okay, now the drawing is not the best one, but could have done better. Let's say in this case, this is considered as a fixed point. So this is not fixed, this is a restraint. So the displacement is, it cannot go anywhere because we have this other member. Okay? Now, in your opinion, where the Barclay verification will be critical? Will be around Y or around Z? Can we say a priori which one is the most critical check? Around Y or around Z?
Around there.
The first.
Around Z or around Y? Z or Y?
When we consider the entire L, not divided.
Here we consider the entire L, but we have a D divided square root of 12. So here the numerator is higher, but also the denominator is higher. Here the numerator is lower, but also the denominator is lower. We need to understand which ratio prevails. A priori we cannot say. Okay? Would it be different instead if we would have a situation like this? No, I can't write it because I have ruler. In this case, you know a priori which kind of buckling is worse. So let's say that in this case we call again like before, call. Well, if you do the same symbol, we call this one Z and this one Y. Where would you expect here to have a proper buckling? First. Around Z or along Z? Because around Z means, if you say around Z, it means a buckling like this. If you say instead along Z, it means a buckling like this. Around Z is the most critical, in your opinion. What do the others think about it? Along Z or around Z? Around? Seems that most of the people from this around Z. Well, in this case, you see, in this case, you would have something like L divided by B over square root of 12. And here you would have L. Now forget about the subscript here. One case would be, okay, let's put the subscript. This lambda y, which means around y, lambda y, would be around y means that you have L divided by 2 divided by B, around y is B divided by square root of 12. Instead, LZ would be L divided by B over square root of 12. Which one is larger? The second term, the numerator is twice as much as before, and the denominator is lower than before, so the ratio is higher. So basically, the right answer was, in this case, we are sure that the critical buckling will be around Z. So, this buckling out of plane, okay? It's clear? Because if you look at the ratio is much higher than the other one. Are you convinced? I don't see you much. Some of you, yes, but not all. Chiaro? Quale?
Cosa intendiamo per il È la seconda.
Allora, andiamo a vedere. Nella seconda figura, se abbiamo fatto giusto, questo è D, questo è D. Vediamo se ho fatto giusto. Lambda Y ci sarà un Y. I would like that you really understand very well this example, because in the course, very often you will have to make some choice in your design, some choices about the buckling length of your members. Because unlike reinforced concrete, in timber, almost always the design is governed by buckling or by serviceability limitation. Not much strength. So we need to be very sure about what you consider as a buckling length, axis or rotation, so on. Is clear? Are those two examples clear enough? Any question about this? Then we try to finish this topic about flexural buckling. So here you have basically the radius of gyration. Note that if the relative slenderness, you see this value here, relative slenderness is less than 0.3, then you can ignore, you can neglect flexural buckling, because it means that your structure is stiff enough to buckle. The other important thing to note here, we already mentioned this, in this formula to calculate the relative slenderness, you need to use the characteristic compressive strength parallel to the plane, but also you see the Young modulus. So the Young modulus is going to affect the Euler load, as you know very well. And here, since we are talking about an ultimate limit state, we need to use the characteristic value of the Young modulus. So E 0.05 is the characteristic value of the Young modulus. You could ask me, but why, when we design with steel, when we design, for example, steel columns loaded or subjected to buckling, we don't use the characteristic Young modulus of steel. We just use the normal Young modulus, 2,100,000, what it is. 210 gigapascal, always the same for deflection and for buckling. Well, instead, for timber, for deflection, we have to use the mean Young modulus. Instead, for buckling, we need to use the characteristic value of the Young modulus, which is lower, because if you go to C, around in the table, you see, fifth percentile module of elasticity parallel bending is, for example, for C18 is 6. While instead, mean module of elasticity parallel bending is 9. So we're using Young modulus which is 1/3 lower for the buckling. Instead, for steel, when we do the buckling verification of a steel column, we always use the same Young modulus, 210 gigapascal. Why is that? Any idea why? Well, the anisotropic behavior is already been taken into account because you have a different young module in one direction and the other. Now we are checking the one parallel to the grain. And we have two different values. One is that for steel, we use only one. Why is that, in your opinion? Because also for steel, strictly speaking, when we do the buckling verification, we should be using the 5th percentile of the young modules of steel. Why is that for steel we don't care about this, we use always the same, with 210. In bending and 210 in buckling. Any idea? What's the most important, one of the most important difference between the steel as a material and timber? The defects?
The Gauss is more...
The distribution, the scatter of results. If you remember, for the probability density, let's say, the distribution function of the module of elasticity of timber is much wider compared the probability density function of steel. So for steel, the difference between the 5th percentile and the mean value is negative. One is 110, maybe the other one is 290. 1% of difference. For timber, no. For timber, you can see it's 50% of difference. So for timber, this difference is significant, so you need to take it into account. Okay? Now let's try to close this topic and to finish this lecture. Okay, this comes from the theory that you already studied in structural mechanics. So this is the Euler curve, and you see this red dashed curve is slightly different because it takes into account that in the reality we don't have a perfect beam, a perfect column, but we have a column with defects, initial curvature, some eccentricity or loss, and so on. So, according to the Euler theory that you studied, I should assess sigma C0, so the strength demand in terms of stresses parallel to the brain, and it should be not higher than the critical stress, calculated with the Euler formula. Critical stress, you see, is critical load divided by A. The critical load, according to the Euler theory, is pi squared times, we said, the 5th percentile of Young modulus times second moment of area divided by buckling length squared. Then you see here you can write that I is equal to area times rho, which is the rho square, which is the radius of gyration. And then in the end you see we end up with this relationship here. Pi squared times Young modulus divided by slenderness ratio squared. This one can be also at the limit curve, this one is equal to Kc, this reduction factor that we saw before, times Fc0t. The slenderness ratio is L0, buckling length. The buckling length can be expressed as a product of the actual length times a restraint coefficient, beta. And then you see, to find this point here, so this is the intersection between the Euler curve, sorry, this one, the black one, the Euler curve, and this curve here, which represents the strength, the compression strength. So pi, the equation of this curve is pi squared times E divided by lambda equal to Fc0d. So in this way we can find out this limit value of the slenderness ratio at the intersection between the Euler curve and the curve representing the strength, the compressive strength. So if you solve this equation, you find you see lambda limit pi times square of E divided by Fc0d. And then you find this relative slenderness. Lambda divided by pi times square of Fc0t divided by E005. This relative slenderness ratio is the one that we saw before by the derivation. So this one, see? So this one can be obtained using the Euler formula. restraint coefficient. In general, we usually consider beta equal to 1. Particularly with timber. With timber, it's very hard to get a fully fixed connection. With timber, it's very often we're going to have pin connection. So for timber, very often we use beta equal to 1. Of course, if you have something like this, like a pole where you have a kind of flag, then in this case there's a cantilever. In cantilever, then beta should be equal to 2. So we need to double up the length of the member. Of course, this equation here, I'll show you now. This equation have been derived by considering the defect from wood, and those coefficients being calibrated on experimental tests. So basically, in different parts of Europe, they've done several tests on timber, considering different slenderness ratio, and then they find some fitting curves to determine the dependency of Kc over lambda. So, compression parallel to the grain, we need for the verification, and 5th percentile module of elasticity parallel grain. Remember that in this kind of verification, you need to use the module of elasticity parallel to the grain, not the mean value that we are going to use for the deflection, but what is called the 5th percentile, the characteristic value. Okay? Any question about what we saw today? Please try to see again if you have doubts about this concept here, because it's very crucial for this course that you are able to understand without any doubt what are the right buckling length to consider in the verifications. Okay?
Nella sezione di lato, le volte l'altro, i due lambda diventano uguali, la z e lambda y, e il bulk invece cioè dov'è?
Allora, so the question is, repeat the question, if you double up what?
If, for example, B is 2 times B.
Okay, so B is twice D. So you rather than having a rectangle in this way, you use a rectangle the other way around. Yes.
È possibile che lambda y is equal to lambda z.
Yes.
Where is critical?
I need to see case by case. So what you're saying, okay, assume now that B is equal to this one is equal to 2D. So if B is equal to 2D, it means that we are talking about a rectangle like this. This one is like if it was this way. So B equal to 2D.
It's not important that B is equal to D or vice versa. Then my question is,
Yes.
lambda z is equal to lambda y.
Yes.
What happens?
Okay, if the question is, if I have the two lambda z and lambda y which are the same, what can we say in this case? Where is going to buckle? We don't know. We need to do both checks. In the reality, we don't know where it's going to buckle. Maybe one side, maybe the other. The probability is exactly the same.
Quindi vanno sulle tutte e due le direzioni.
Yes, but because they are the same.
Ah, quindi anche se una immagine di un'altra.
No, okay. Let's put it this way. If you can a priori recognize that one is larger than the other, you do the verification only for the one from the larger one. You don't want to lose time for the other. If you see that both are the same, then you take either one, because they are the same, and you do the check. After you don't know in the reality where it's going to buckle, because you have maybe there is a small defect you don't know in one direction, it's going to buckle in this direction there. Anyway, the idea is that for timber, but also for your design, that you should implement those formulas. This one, the best thing to do is to implement those formulas into an Excel spreadsheet, of course, like you've done for instance for design. And after you have all the formula in an Excel spreadsheet, immediately you see where it's going to buckle. Because if you memorize both of them, then you do automatically both verification, both checks, and you see immediately which one is the most critical one. Okay? But a priori it's important to recognize anyway. So the most important thing is actually to choose the buckling length in the right way, like we were saying here. The choice of the right buckling length is very important, otherwise we get completely wrong. Okay?